Welcome to the latest episode of our PiXL Drone Show, our weekly podcast covering fascinating people who do cool and interesting things with drones. My co-hosts for today are Kara Murphy and Greg Reverdio, the same crew that I'm sure you guys know by now. And our guest is a fellow Dutchman, Bart Duisterhof, and he's a graduate from the Technical University of Delft, which basically is the Dutch version of MIT, if you will. And he received an honorable mention as best graduate of the Faculty of Aerospace Engineering. And Bart came up with an idea or a way to use a swarm of small drones to detect gas leaks. And we're going to definitely talk about that a lot more in a minute. First of all, welcome to the show, Bart.
Yeah, thank you, Hi, for introducing.
Awesome. Well, we're going to start off and basically get to know you a little bit. Can you tell us when you got started with drones and how you got started flying drones?
It was actually I think I was about 19 years old back then, in my second year of the bachelor program in aerospace. There was this research program that we could participate in. And there was this one professor, his name was Guido de Kroon, also the other author on this on the gas leaking work. And I just kept asking him, like, can I do some cool stuff with drones? And eventually he gave me a drone, and I could play around with it in our playroom, basically. So like try to write code for the drone and stuff.
That's pretty awesome. So you were actually able to use drones as part of your studies at the Delft University?
Yeah, so there's some extra credit. There's an extra program with research. So it's not part of the normal curriculum, but as part of this extra program, I was able to work with drones.
That's cool. That's awesome.
So I've seen a lot of self-made entrepreneurs in the drone industry. How would you say a university curriculum prepares students or would-be professionals in the drone industry? Is it necessary? Do you think it gives people an edge?
I guess it depends on what sort of position you'd want in the drone industry. But what I think is very useful is sort of this practical experience with coding on an embedded system and using a drone. So knowing, like, I can just speak from this like software engineer perspective, and I think there definitely experience helps. So we used to have this course, or there's still the course being taught by Guido that just really gives a hands-on experience with flying a drone with the camera and trying to avoid people and obstacles. It's a lot of fun, and I think that experience is super valuable for any drone company. Just getting your hands dirty, basically.
That's cool. So during your time in Delft, you had a project in which you used a swarm of smaller drones that are able to detect gas leaks. Can you tell us a little bit about that project and how that got started?
Yeah, definitely. So there was an earlier project where we did light seeking. That was the year before, in 2019. And after the light seeking project, we thought about ways that we could improve this and make it more useful. And in that way, like starting from that starting point, we started thinking about multiple drones instead of just one, and looking for a gas leak instead of a light source.
So, what kind of drones did you guys use for this research?
We used BitCraze Crazy Flies. So it's about 40 grams. Our platform was 37 grams. And it can fly for about 7 minutes. But it's just a research platform, so probably if you would spend more money, you'd get those numbers up.
Yeah.
So are these drones customized or are they pretty much off the shelf?
So the basically how this works is the BitCraze Crazy Fly is a small Swedish company that makes a research platform, or platform for people that like to play with tiny drones in their homes, and you can basically add decks on top of the system. So there's a base system that also forms the structural integrity of the thing, basically just a printed circuit board with a microcontroller. And there's all sorts of decks that you can add on top of it that they also sell. So for instance, we used laser rangers, like a laser ranger deck that they sold us. And then there's an optic flow sensor for some form of state estimation. So basically this system could already hover in place without us needing to change anything from the hardware. But what we did was we added another deck that we designed, another printed circuit board, which was very easy to do thanks to all of their open source code. And then we added a gas sensor and something called ultra wideband. So there's these two things that made swarming possible. So with ultra wideband, the technology is similar to the recent Apple AirTags, where you can estimate the relative position between drones without any external systems. So that's something that we added to the board, and then we added a very tiny gas sensor. So part of it was custom, but most of it was readily off the shelf.
How long did it take you guys to basically use those parts and make it into a functional drone to detect gas leaks? Like, how much time was involved in figuring that out, how to make that work?
I think, like, you mean purely the hardware prototyping, right? I think that was about two months roughly. Like, I first soldered something on a prototyping board on the drone, but every time I had a small crash, everything broke. So at that point, I just decided, or we just decided to put everything into a nice circuit board. So that's
cool.
Roughly how long it took.
And I can imagine, I mean, if you look at, let's say, more regular drones like Autel drones or DJI drones, you have the DJI Mini. Autel came out now with the Nano. And whenever I talk to those companies, they always say that when you make things smaller, things get exponentially more difficult and harder to manufacture. Did you guys have a similar experience where trying to make that roll so small and so light, it was actually something that made it more difficult or more challenging, perhaps?
One part of it is that the gas sensors get really bad at this scale. So the size of it is like a couple of millimeters. And you use some other components to actually read it out and heat it up. But definitely, it's a big challenge to obtain useful information from a sensor that's so noisy and drifts over time. Like, you basically think there's a gas if you only look at the readings, it goes up over time. So to be smart about the decisions you make based on such a bad input.
Is there benefit for the drones to be so small and light, or would you rather have had larger drones with better gas detecting sensors?
Yeah, so we're focusing on indoor places, and for indoor places, of course, you need to be smaller than a door, for example. But that's still pretty big. The reason I think small is good is because it's very low cost and it's very safe. So it becomes way easier for it to be deployed. So we want to build something that will one day replace a person, or well, maybe not replace, but make the job of a person much easier. Then I think it needs to be much better than just doing it with people. And maybe if it's safe and super low cost, then it could be a reality.
Yeah.
With the sensor on board, are you worried at all about the prop wash pushing away the gas, or is that strong enough that the sensor is sensitive enough that it would pick it up anyway?
Yeah, that's a great question. It could go either ways. If the gas source would be above the drone, then you would basically suck in the gas and it would be better. But if it would be under the drone, then maybe indeed it could get pushed away. But I do think it's a much less pronounced effect for something this small as compared to a bigger drone. We were building a DJI-sized drone the other day, and it's just your clothes start moving based on the like if you let it take off inside. So it's really a significant amount of air being moved. Whereas this thing, like, you can basically, it's so safe that you can just grab it out of the air if it doesn't respond anymore. So yeah.
A couple of years ago, was it the LA, Los Angeles Fire Department, and they had a DJI Matrice drone that was outfitted to detect gas, but they had an entire extension rod basically attached to the drone, so they could sniff out gas at maybe 4 or 5 feet away from the actual aircraft, and I think probably to counter this issue as well.
Oh, that's interesting. Yeah.
Yeah. Would that work with smaller drones, you think, if you had like something like a straw almost to kind of get away from the prop wash, or no?
Maybe. It's just that the control effectiveness, like how much extra thrust it can generate, is limited, and also the added weight would be consideration, and I guess also robustness. Like, you would make something that's very tiny, very slim. So I'm not sure if that will probably break if you push it too much.
Yep.
So how does this idea come up? Did you read a paper somewhere maybe that was talking about gas leak? How did you guys decide on this specific idea?
So so we started. The starting point was sort of that we had thought about sort of ways to use insect-inspired AI for useful tasks on tiny drones, because we would really like to see tiny drones do useful jobs. And then this gas seeking field seems pretty huge. Like there's a number of researchers and entire research groups working on gas seeking. So yeah, we thought it was super cool to try, and some papers were hopeful and some other papers were more pessimistic. So we thought it was a good open research problem that was somewhat risky, but eventually it turned out well, and it was actually pretty cool to see it work this well for the gas sources that we tested.
Awesome.
Yeah. In your research paper, you refer to a bio-inspired algorithm. Can you explain to us what you mean with that and how that works?
Yeah. So the algorithm that we developed is called SniffyBug, and so the Sniffy is just a reference to it's sniffing a gas source, and we call this a bug algorithm because it follows a set of few simple rules. This comes from sort of the animal kingdom from insects, where it's observed that insects use very simple rules to complete complex tasks. And for gas seeking, for instance, there's these silkworm moths that are very effective at finding female silkworm moths based on the pheromone that they release. And to do this, they it's a super complex problem, but they use a very simple strategy in the end by sensing the wind and flying upwind and stopping flying upwind, basically.
Mm-hmm.
But the only issue or challenge is that we can't exactly recreate insects, and we may also have different objectives. So, for instance, in this work, we have multiple agents, so we're using a team of robots, and insects can't really collaborate. So we basically designed our own set of rules, and then let our evolutionary algorithm change the rules a little bit to make them more optimal. And that's sort of that's where where the term bio-inspired comes from.
Okay, so I mean, it sounds on one hand like, oh, that this is really simple because we have a few simple rules, but then at the same time, this is a self-evolving and learning system, and I guess the part of the complexity is the fact of how these rules work together. Can you give us some examples of the rules that you guys used in your drones?
Yeah, totally. It's when we first started thinking about these rules, we also thought it would be easier than other strategies you would normally use. But it turned out to be actually pretty hard. So the challenges are avoiding obstacles with very limited sensory inputs. So we're using these tiny laser rangers in 4 directions, and it's pretty limited compared to what you see on larger drones, which you guys have seen, the LiDARs and stuff.
Mm-hmm.
So some of the rules are focusing around avoiding obstacles and walls, and it's more clear from the figures in the paper. But basically, what we do to let drones avoid each other and obstacles at the same time. So let's say that they cross each other in the corner of a room. We simulate some sort of repulsive force, like magnets, away from the walls and away from other drones. And this is a very simple way to do a pretty complex coordination between different team members. So you would see them basically crossing each other close to a wall, and then magnets move, move in different directions, which is it's a super simple way to solve a somewhat complex coordination problem.
Yeah.
So why is a drone swarm important for finding gas leaks?
I think the people I talk to in chemical plants and in harbors, it seems like it's a very manual task nowadays. So people go in with a handheld gas sensor and just try to find the gas leak manually, which is cost prohibitive because it's downtime for the system. But then there's also danger for the people that go inside. And we think that the larger the team of robots is, the quicker you can find it. So each drone needs to be cheaper and safer. So That's why we want to use small drones to quickly find the source.
How big of a team of like how many? What's the biggest you've ever deployed?
So I think in the lab that we developed this in, I think the largest team is 7 at this point. But there's some work at Harvard where they used, I think, hundreds of tiny walking robots that are even more limited.
So you mentioned earlier in the conversation that this is for indoor use. Is it indoor use only because the drones are so small, so lightweight, or could this potentially be used outside as well? And can you give us some examples of environments that you guys have used these drones?
Yeah, that's also a great question. I think the current setup, like the current control system and exact drone, would be very challenging to operate outdoors because it's just so light. The control system is really designed for outdoor use. But it is, we know it's possible to use these things outside because there's other systems that do work outside of this scale. Something called a Black Hornet, which is not like observation drone for army. It's a much more expensive system, but it seems to work really well outside, even in more challenging wind conditions. So we haven't really tested them outside because of this relatively cheap research platform just doesn't really like wind. But there's good hope that systems can be developed at this scale that do work outside.
So how large of an area are you able to cover?
In this example, we covered our testing area was 10 by 10 meters, so that's I guess 30 by 30 feet, which may sound small, but previous work that we referenced is like even smaller. Like they would try this in a wind tunnel, for instance. So we would have 10 by 10 meters and with walls and obstacles. But the optimization strategy that we used, we think is capable of much larger areas in future work.
So I'm thinking about this. I'm thinking about one drone flying in an unknown environment, right? Flying into this room and having to detect obstacles and detect other things. Now you're talking about a swarm of drones having to do the same thing and also kind of deal with each other. That sounds like a big challenge to me. Is this something that you found was pretty difficult to do?
So I think because of the system that we use for detection of other team members, the avoidance between team members was somewhat doable, but the avoidance of obstacles at this scale is very challenging. Even for larger systems, this is many times this is still very challenging. But for such a tiny system, it has just such poor sensory inputs that it leaves a lot of guesswork. Like very slender obstacles like cables or ropes, they're just almost impossible to see for such a system. It's sort of our philosophy is that hopefully, we're expecting some of them to fail, but it's not that much of a big deal to crash a drone of a couple $100 or euros by comparison of crashing a drone with carrying a LiDAR of $30,000.
Yeah. So I was actually going to mention LiDAR because more and more drones, it seems like LiDAR is getting more and more affordable, and having LiDAR system to detect obstacles and even other obstacles that are flying around might be easier, but obviously you're trying to stay small. So is this ever something that you either would want to do in the future or something that is just too big and too expensive to put in there?
Yeah, that's also a great question. I think there's research in novel sensors that needs to happen, and for instance these the LiDAR sensors in the new iPhones are very small now. Yeah. So I'm thinking if this market gets larger, then manufacturers will make some stuff that's smaller and more affordable, and definitely that would be super useful, especially if you want to fly in the dark. So we could use cameras, but cameras, especially at this scale, would be a challenge to use if you're flying in very poor light conditions.
So if you have a swarm of, let's say, 7 drones flying in a 10 by 10 meter or 30 by 30 feet space, and there are smaller, thinner obstacles like cables or wires or whatnot, if you happen to crash, let's say, 2 out of the 7 drones, does the rest of the swarm just continue the job just with fewer drones, or how does that work?
Yeah, this is something that we didn't incorporate in this version, but it would be pretty easy to incorporate it. So like basically now we have a very fixed communication protocol for our experiments, but it would be fairly straightforward to, like, as long as you can detect that you failed, which is usually like a very big spike of acceleration, or you're laying upside down on the ground, these sort of things. As long as you can detect that you failed, it should be definitely be possible to continue with the other members of the swarm.
So that kind of leads into my next question. And I was going to ask you, like, okay, these drones fly autonomously. What is the role for a pilot? Like, does somebody just press a button and the drones take off and do their thing, or are they somehow actively managed still? And also, I'm curious to learn more about, you mentioned just now that these drones communicate and you have very strict communication protocols. Do they know where they are relative to each other, or how does that work?
So I would say if you have a fire of some sorts, then it would be great if there's a ground station where someone basically just presses a button for them to take off and get some information feedback. But this is generally hard because you get into some space and may not be possible to communicate back. But that would be the ideal case. Maybe you have some driving robot as well that sort of sends back signals. And then for the relative localization, they have some sort of estimate of where the other people or like the other team members' drones are, and it's generally pretty accurate. And they do not only use it for avoiding each other, but they also use it for being more efficient in collaborating. So basically, you tell me, like, you're in the kitchen and tell me that you smell bacon, then it would make sense for me to look in the same direction.
Bacon smelling drones. I think we're onto something here.
A new market.
A new market, exactly. And then your alarm goes off, so you jump out of bed and run to the kitchen. So in your in your project, the drones that you flew, like, can you talk us through the startup procedure? Like, if you wanted those 7 drones to take off and do their job, like, what was involved to make that actually happen?
So you would let the drones first sit on the ground, and basically tell one of them, like they're all in this communication scheme already by the time that they're turned on. Then you tell one of them that it's time to go, basically. So they all take off, and they do some sort of initialization pattern that initializes the relative localization. So the way relative localization works is telling each other in which direction you're moving, and then sensing if you're getting further or longer away. Because radio beacons only don't tell you a direction, only the distance to a different person or to a different drone. So telling each other what you're doing over time, together that information will help you to figure out exactly where the other people are. So we have an initialization procedure to let that system converge. Then they start exploring the room. As long as none of the members of the swarm has smelled any gas, they just explore the room entirely. And then once one of them has smelled the gas, they start looking for the source more directly. So they don't all just go and fly to that one position, because we actually want to find the source, and maybe we're just still very far away. But we use this algorithm called particle swarm optimization. It's based on birds, like the patterns you see by birds, and they get closer and closer to the source over time by doing this algorithm. Then they find the source, and they hopefully stay close to the source, or still explore a bit if they're not confident enough.
Is there a limit to how far away they can fly from each other?
No, there's no limit.
Okay.
But there's they may at some point would be hard to estimate the location of the other members, because they don't sense this radio beacon anymore.
Yeah. What distance would that be? Would you estimate or guesstimate?
I think
Worst case scenario.
This is actually something we looked into, because you can sort of set different power for the ultra wideband sensor, for the radio sensor that we're using. And I think that they're rating this for up to 70 meters or something. So yeah, that's a constraint. And then at that point, it would also be harder to communicate with other swarm members. But our this is one of the questions that actually came up in my thesis defense for this work. Is like, what would you do if you want to use 1,000 of them? And the sort of the idea we have is to have local interactions. So you only communicate with the drones that are closer, but you can't communicate with 1,000 drones at the same time because that would just be crazy. So like local rules.
So if you have, let's say you have 1,000 drones in one swarm and you subdivide them in smaller groups that are in close proximity, and then basically they're subgroups. Is there like a central intelligence point where all the information is collected and gathered, or is it just within the group a collective of brains, let's say, per drone that function decentralized?
It would be fully decentralized, at least in the way we currently do it.
So you mentioned open source autonomy. Why is this so important to have this open source?
Yeah, I think it's still very hard to make a system autonomous these days, especially robust autonomy. And it would be great if it would just be very easy to make something somewhat autonomous. So I think it's super important to upload our code to GitHub basically, and to allow other people to read it and maybe use it in their own projects. So eventually it would be great if the autonomy that's available in an open source way is just as good as that companies have access to. But that's of course they may not want to upload their code to GitHub if they spend a lot of money on developing it.
Yeah.
I guess that might make sense. Now, I know when you fly drones in the Netherlands, the drone regulations are similar, but yet still different from the rules and regulations we have here in the United States. When you fly a swarm of drones indoors, do you have any rules that you need to factor in? And if you were to take this outside at some point, how would that work?
I guess you definitely have this beyond visual line of sight problem that we have here. I haven't really thought about that much, to be honest, but I do think, I wonder, do you think you could fly them if you're just looking at them and you basically have a kill switch? I think beyond visual line of sight is usually still hard to do, right?
Yeah.
So like sending them into a building.
When you fly indoors in the Netherlands, are rules not applicable?
Indoors, no, I think definitely for the smaller drones. Like there's some safety guidelines that we need to stick to. Like there's nets around it and people are wearing glasses and stuff.
Yeah, that makes sense, I guess.
So what is involved in the drone's ability to sniff gas? Like what kind of technology is involved, I guess? Like how do you get the drones to, I guess, detect or identify gas leaks or the gas? That makes sense?
Yeah, that makes more sense. I think maybe just to start from the input, it's a very tiny, low-cost gas sensor that usually comes in fire detectors. So it's able to detect all sorts of different things that could be dangerous. In our case, it was actually finding alcohol. So maybe there's some business opportunities there to find cans of alcohol. But there's a signal that comes in, and the first thing we do is we're trying to classify if it's a gas source or if it's just noise. Once we've decided there's gas or noise, we make different decisions for the system. And we're constantly passing around this in the swarm, so the entire swarm knows everything about everyone, including their position and gas readings. So once all of that information is available, we're either exploring or seeking. That's the names we give to the different strategies that we deploy in the system. So the exploring mode, they're just flying in different random directions, and they're trying to explore different rooms if those are present. And when we're seeking, we're definitely being more direct into finding a different area. So maybe one of them has found some gas in one area, so they're being more directly searching into that area. And the main, I guess, difference between more traditional systems or systems with SLAM and cameras is that we have come up with rules to avoid different obstacles, agents, and walls and such that are inspired by some insects, instead of using computational solvers based on an entire map of the environment, because we couldn't, like, the computational resources available are maybe up to 1,000 times more constrained compared to your mobile phone. So we really can't do anything. So what we end up doing is following a set of simple rules instead of making an entire map of the environment and finding the closest path to a goal waypoint. So that is, I think that was a big challenge.
So you said there's a seeking mode. Does the seeking mode happen when one of the drones detects gas, or is that just a mode that you can program for the drones to go seek a specific area?
It is just if one of the drones detects gas. So if one of them detects gas, then it makes sense for the other drones to also start looking into that direction.
Into that area.
Yeah.
Yeah. And so if the other drones also detect, then is that a confirmation that there is something there? Then what happens? Is there an alert going to the operator? Is that data just being recorded? What's the next step? Because I'm sure there's an actionable item that you want someone to go check that area manually. What's the procedure there?
So what we did for now is there's different lights on the drone. So if one of them detects gas, it starts flashing. So that's one thing we do. But the other thing we do is we change the paths of the system to slowly start exploring. So on one extreme end, you could like fly to that one point where we found some sort of gas and just wave your hand and ask a human to come in. But we would like to, like, in practice, we saw that gas can disperse very far. It can even go around corners, and it would be really useful to find the highest concentration of gas. So basically what they end up doing, the result of our algorithm is that they start exploring around the point where they detected gas. And this is done in a random way. So you wouldn't want to get stuck in this point where you detected once gas. Maybe it was random, you know.
Have you guys been able to test your gas sniffing drone solution, if I may call it like that, in any real life situations outside of a lab or outside of, let's say, the university in Delft?
We have made a video. There's a video on YouTube where we tested drones in a warehouse. So like most of the testing was done in our testing arena. It's 10 by 10 meters in size, but there we tested in larger environments with some complex, like with chairs in the environment and some other cool features. So, but yeah, this is something we talked about to try and see if it works in larger environments, and if not, like what modifications would need to be done to make it better in these cases.
So do you have plans to bring this solution to the market?
I don't have plans to bring it to the market, but yeah, I think it could be. Yeah, I have no idea how large this market is, and how robust it needs to be. So there's like we're thinking that if you make something smaller, it needs to be less robust because it's more okay for it to fail. But I'm not sure how other people think about it. Maybe they would rather have one system that's more robust in a chemical plant or something.
Yeah, that makes sense.
So,
do you see any other applications for the drone potentially to do other things than just detect gas?
there's one cool thing. People in the harbor of Rotterdam told me this: detecting drugs would be very useful. So there could be drugs in all the containers. So like to actually seek for illegal substances, but maybe a bit more, somewhat more straightforward could be asset tracking. So there's some drone companies that have started asset tracking in warehouses, and maybe smaller drones would be useful there as well. I guess most of the things we do with larger drones now would be cool to do them with smaller ones that are cheaper. But there's of course innovation that needs to happen on every, like on all sides. Better cameras at a small size and these sort of things.
Yeah. So now that you've concluded this project and you learned quite a few things about drones, what kind of other project might get you excited to look into with all this new knowledge, let's say?
What I'm looking into now is using cameras. So what I learned in a previous project is that the sensor you're using matters a lot for how successful the system is. especially for what I just mentioned, for detecting these power lines or shallow obstacles, like to be more robust in general. I think it would be great to use a camera. So
Yeah.
thinking about ways to use a camera on a very tiny system.
Yeah, I know from first-hand experience even that obstacle avoidance, even among the newest drones like the Mavic 3 and the Skydio 2, is when it comes to like thin lines or cables or branches, it's hard to detect, and also it's not just dependent on the size of the object, but also the lighting conditions. As it gets darker or the sun is lower, it can be really tricky to avoid that. Yeah.
Yeah, definitely. And like Skydio still has 3 cameras in each direction, so
Yeah.
in large baseline, relatively speaking. So it's a very exciting area to think about, like learning solutions and new solutions to estimate that depth, basically, which is doesn't seem super trivial.
So, as I understand it, you are currently in the United States. What are you doing right now, and are drones still involved?
Yeah, I'm currently in the Robotics Institute at Carnegie Mellon doing a PhD in robotics. The group I'm in is called the Air Lab, and it's basically all that we do is with drones, or almost everything. They also participated in this in the DARPA subtraining challenge, where they also used some walking or driving robots, I think. But yeah, for my project, we're looking into tiny drones and computer vision applications, or computer vision algorithms to make navigation better.
What attracted you to Carnegie Mellon's program in particular? How did it get your attention? How did you discover it?
I'm originally an aerospace student, so I studied aerospace engineering in TU Delft, and I felt like it would be great for me to join a more computer science oriented program in robotics to learn more about the theory behind why some of these computer vision and SLAM and autonomy algorithms work. And it seems like the basic sort of mathematical foundations are in some way similar between aerospace and computer science, but there's definitely a lot to learn. And I'm taking super interesting courses here. So
Yeah, I mean, it is a top tier school. And you've obviously done well for yourself, but I can't imagine that tuition is quite hefty. Did you earn a scholarship, or you're just able to fund it yourself? I know how expensive American university can be, being a graduate myself.
yeah, so actually, after the bachelor's program in TU Delft, I considered going to the US for a master program, but I realized it's just insanely expensive, basically. So yeah, so for a PhD program in STEM, you're usually like, or the programs that I've looked into, you're fully funded. So I receive a stipend, and my tuition fee is fully covered by the research I do, basically. Yeah, the tuition fee I would never be able to afford.
Yeah.
So um,
And
yeah,
I wasn't suggesting you couldn't. I just know, as an American university graduate,
right, yeah.
that there are programs for a lot of people which are really helpful and great. But I'm always curious about people's academic journeys, just because everyone has a different story and something to share. So thank you.
Yeah, I totally understand, and it's quite weird to see the difference in tuition fee and how it works here compared to the Netherlands, where tuition fee is like 20 times lower. Like, I think 20 times lower than here.
Yeah, I'm working on getting my daughter dual citizenship in Scotland, because
Oh,
university is free over there, and she could even get a master's or PhD free of charge. It's quite crazy how other countries have this figured out. But anyway, I'll let Haya get on to his next question. I just have to
yeah.
put that out there.
Yeah, but my next question still has to do with students. I think for the drone industry in general, it's important that we keep like new talent flowing into the industry. And I was curious, since you're a student and you've been working with drones at a university level, do you have any ideas or any advice that might be helpful to make drones more accessible to students, or to advise schools as to what they might do to make it more interesting for students to get into the drone industry?
Yeah, that's another great question. I think you actually don't need that much if students are interested enough. So if you'd have drones that are hackable and that can be flown somewhere, and the students are interested in using them, then I think that's more or less all that you need. Maybe some guidance from a teacher that knows what they're doing. But like from my experience, there's really it's really useful to get your hands dirty and implement something on a drone. It's just for me that really worked to make me even more excited about these things.
Yeah.
So to type lines of code, and then like I didn't understand any of like using terminals and like all the computer science stuff, but having like maybe that's one more important thing, is to have enough interesting like people together that are interested in the same things, because there's so many people that helped me out initially to get things set up and to get going. So it's really hard to figure out everything on your own.
Yeah, I can imagine.
So there is there's a course that, like, I think I talked about it in the start of this at the start of this podcast, and that was just a course where they really gave us the basic tools we needed to get started. And from that point, I think everyone could just explore their interests better.
Yeah. Was this mainly your project, or was this a team effort, and did you have people to work with other than, let's say, your direct teachers?
Yeah, this was mostly my master thesis. Of course, I did have some help for like supervision and for asking questions, and especially the like designing the printed circuit board was a challenge. For helping with testing and making sure hardware works.
Yeah.
But it was like majority of it was definitely my master thesis.
So it's about 6% women in the drone industry. That percentage is kind of held the past few years. And so I'm the one that asks these types of questions here and there. Do you think there is a need to get more women involved, especially in your field? And how do you think we should go about that?
Yeah, that's also a great question. I know that the TU Delft is very involved with that. Like I've seen different statements from the dean saying that they're trying to get that up. I think what they're doing here is there's a program called Women in, or Girls of Steel, I think it's called, where they're trying to. So this is called, Pittsburgh's called the Steel City, and they're trying to find girls that are interested in STEM and let them do cool stuff at CMU, and hopefully also give them some better chance to get into the program later. It's hard for me to judge like what is most effective.
Yeah,
I guess, but
I did not know about those programs. That's really interesting. So we should try to get links. You can edit this out, but we should try to get links in the show notes.
I do know CMU also has a 50% policy now for undergrads at computer science. So they admit 50% female students.
Oh, we are making progress.
Yeah, I guess you need examples of other successful women in the industry. Yeah, it's hard. I guess hard to know what is most effective, but there's different things I guess that we need to do. It was the same in aerospace, in my aerospace studies, to be honest. I think it was also exactly 6%, which was actually the guys were very sad about, because there's it's only guys.
Lots of guy time, right?
So as we get towards the end of the show, we always ask our guests that one question, which is, what's your favorite drone to fly?
That's also a great question. I think I must say I haven't flown that many drones. I think the DJI drones are a bit boring for recreational purposes. I like flying more tiny drones. Like I flew in an FPV. I think it was a trash can drone a couple times. I think that's pretty exciting to fly indoors and annoy people in your home. Um, a bit more easy to fly than, or easy to start flying than like a big 5-inch FPV kind of thing.
Yep.
Like the smaller Cinewhoops, basically.
Yeah,
Yeah.
these sort of. I think they're super fun.
Yeah, they're super cool for sure. Well, Bart, congratulations, of course, graduating from TU in Delft and continuing your education here in the United States. Thank you for being on this show. It was a real pleasure talking to you.
Yeah, thank you so much for inviting us. Great to talk to you about all these things.
Yeah, it's awesome. It's always cool to. I mean, I think that's for the three of us what attracts us to hosting and doing this show. So we get to talk to all these interesting and cool people who do pretty cool stuff with drones. And we've had a large variety of different projects and different people doing cool stuff. So we're happy to continue this show for sure. For everybody out there listening to this show on the podcast or watching it on YouTube, if you want more information about Bart and his project, we'll put a bunch of links and a video in the description below. And if you enjoyed this episode of the PiXL Drone Show, please be sure to subscribe and to share it on social media. It definitely helps us to keep doing this and to keep growing the PiXL Drone Show. This episode will air on Tuesday, as we always go live with our shows on Tuesday morning, both on YouTube and on other podcast platforms as well. Thank you everybody for listening, and we'll be back next week.